Okay, so the first one, all right, we've got -3 and -1 and a -2. So it would be up 1 over 1, but it's times -2. Now, because of the reciprocal, you see this 1, 2, I can go 2, 1. 1 point on a reciprocal graph actually gives you 4 points. Here, right? It's symmetric in the quadrants. There's 4 points. Looks like I plotted the x-intercept. Means you didn't actually have to solve for it. It was plotted. Okay. Okay. So I'm not, let's see, vertical asymptote, x equals -3. Horizontal asymptote, y equals -1. Okay. X and y intercept. So I'm going to do the y-intercept first. -2/3 minus 1. -5/3. Okay, x-intercept puts a 0 here. Right, there's not a lot of room here, so I'm going to add the 1 over, cross multiply, -3, so -5. Look at that, -5, 0. Okay, give the function in standard form. Standard form for the ratio of polynomials is just one polynomial on the top, one polynomial on the bottom. And so I'm going to give them a common denominator, -2 minus, okay, -2 minus x minus 3. So we get -x minus 5 over, that's it. There's no reducing here. That's why we did a little bit of the preview. Like, you can't cross anything out there. That's it. Yeah.
Wait, if you're multiplying it by x plus 3, wouldn't that mean you get x plus 3 squared on the bottom?
No. When you do 1/4 plus 1/4, what do you get?
Oh.
Yep, okay. So the denominator doesn't change when you add fractions.
Yeah, that's true. All right.
Okay.
Also, how do you find points other than the first 4 points when there's like a stretch?
When there is a stretch?
Yeah.
This is because of the stretch. So usually I do this. Okay. -1, -1, asymptote, 1, 1. Right? Asymptote's right in the middle of my parent points. And so I'm going to times those parent points by -2. So I get +2, -2. That's what I plotted. -1, +2. You only need 1 point per branch. I happen to put extras because I just counted a few extras. But you only need 1 point per branch. You only plot more as you need to because you're not sure what the shape looks like. Okay? So +1, -2. All right, I'm going to do one from the back side, right? Make sure you have those steps. And then I'm going to write down your questions for the conclusions. Okay. Standard form, right, is just the ratio of polynomials. And we're going to turn it into transformation form. So we're going to do synthetic division. 2x minus 6. You don't have to write it out the long way, but I'm just showing you the division, right? That's what I'm doing. And so it's 2 minus 6, x number. Sometimes synthetic division gets a little tricky to follow when there's fewer terms to look at. So 1, so we're going to bring this down. Okay, linear divided by linear gives me number. So this is number remainder. You've always got to decrease by 1. And so this results in y equals 2 plus the remainder. Now that's not, right, it's like backwards. The k comes first here, but that's still transformation form. So if I wanted to graph it, okay, +1, +2, and a stretch of -4. Okay, I can do stretches without writing out the points. Okay. -1, -1, asymptote, 1, 1. I'm not really going to write 0 undefined every time. I'll just make a note in my table where that asymptote is supposed to be. So I'm going to times it by -4. Okay, left 1, up 1, 2, 3, 4. Right 1, down 1, 2, 3, 4. Can I not add? No, I'm good. -6 plus 2. Okay, so 1 point is fine. Connect the dots. Now I'm going to add another point here because it's like too hard not to. You can also count 1, 2, 3, 4, 1/4, right? But I'm multiplying by 4, so it's going to be a 1. It's actually going to be -1. It's just another easy point to plot. Do the parent and the reciprocal for that stretch. Okay, so here we go. 4, 1, 2, 3, 4, -1. 1, 2, 3, 4, +1. Okay, now I have the y-intercept plotted, so I'm just going to write it down. Transformation form, check. Asymptotes, x equals 1, y equals 2, check. X and y intercepts, so we've got 0, 6, check. X-intercept, okay. Well, it doesn't actually matter which equation you use to solve for your x-intercept. It doesn't. 0 equals 2 plus -4x minus 1. So -2, -4x minus 1. So I get 3. Oh, good. Looks. Can you use your counts to find those points instead? Sure. Okay, I don't care how you find your x and y intercepts. I just care that you can find them. If you're really good at visually transforming points, transform the points onto the intercepts. If that's a little tricky, just plug it in and solve. Okay, good. There's your graph.
Whoa, really?
Okay, we're going to look at the first question. What connection do you see with the horizontal asymptote number in transformation form and standard form? Okay, so I'm going to ask you a few leading questions that might get you to the answer. I'm just going to sketch my asymptotes real quick. So we go here and we go here. Okay, when you have a polynomial in standard form, what gives you the end behavior model? Okay, when you have a polynomial in standard form, what do you look at for the end behavior? I know it's unit 4, but what about a polynomial gives you end behavior? Yeah, so it could be down, down, or up, up. What tells you? Yeah? The degree and A, the leading coefficient. The degree, oh, gotcha. The degree and the leading coefficient. Okay, think about the degree and the leading coefficient of the ratio of polynomials. That means look at the top and the bottom. Leading terms. Okay, I'm going to highlight them. I'll do yellow. Okay, so for number 6, what's the ratio of those two things I just highlighted? -1? You said -1. Oh, interesting. Okay, hold on. Let's go up one. Okay, I'm going to look at the leading term, right? The leading coefficient and the degree of the numerator. Oh, 3. This is why horizontal asymptotes are called end behavior model, because that's all they are. They just happen to be a horizontal line. Okay, so let's go up one more. Okay. Numerator, denominator, ratio of those two things, 2x over x, is 2. And so, if you have standard form, do you have to put it in transformation form to graph it? Not really. You can pick out your asymptotes anyways. Okay, second question. So let's write that one down. What connection do we see with the horizontal asymptote number in transformation form and standard form? In standard form, I'm going to put it's the K number. It's the ratio of leading coefficients and degree. I probably should have said leading term. Leading term is the better description of the leading term because the term incorporates the coefficient and the variable degree part, okay, of the leading terms because it's just two polynomials, which means we have to look at the top polynomial and the bottom polynomial and put them together to get the end behavior model. So if I'm looking at my standard form here, I go, okay, vertical asymptote, boom, x equals -1 because I can see my denominator. I go horizontal asymptote, ratio. Oh, cool. Now I can just maybe just plot a point. Maybe I divide it to get my stretch number. Maybe I find an x-intercept. Maybe I find a y-intercept, and all you need is 1 point per branch. 1 point per branch, that's it. So, how would you find the x-intercept in standard form? And we'll do number 6. You plug in a 0. You cross multiply, right? Same thing as you did with standard form, okay? You cross multiply. What's 0 times x plus 1? 0, yes, 0. Okay, guys. How do you solve that? Don't say isolate. I want to do it a different way. How do you solve a quadratic? Factor it. Can I factor that? Yes, there's a negative you can take out. The factor of the numerator is the x-intercept. How do you find x-intercepts of a polynomial? You factor it. And so this is just a ratio of polynomials. And so if I want to find x-intercepts, I need factors of the numerator. So we get -4. Hey, look. 3, 1, 1, 3. What's my stretch? -3, because I'm in the top left quadrant. Okay. Y-intercept? -4. 1, 3, 3, 1. You don't actually need transformation form to graph. You just have to know where to look to find those pieces. Yeah.
So, couldn't you also, instead of factoring, could you just add x?
Sure. Oh, yeah, certainly. I just wanted to say factors. Right? How do you find x-intercepts of polynomials? You factor them. So I wanted to say something similar. Okay? How can you use standard form to find x-intercepts? Factor the numerator. Okay. Okay, so we're going to start standard form, which we just looked at in our warm-up. Ratio of polynomials. Notice that q of x can't be 0, right? I cannot divide by 0, okay? Your domain, all real numbers except for the denominator being 0. So we might write two different domain notations today, okay? Your range might be too tricky to write, okay? You need an accurate graph to write your range, because sometimes as we move forward, the graphs are going to be a little too hard to write the range, and we'll look at those questions when we get there. So we're going to talk about discontinuities, right? You have to pick your pencil up to draw these graphs. We've already done one of them. An infinite or a non-removable discontinuity is a vertical asymptote. And I'm just going to sketch a small picture of what that looks like. We already kind of know. Right? Vertical asymptote. But we're going to say one more thing. Where does the vertical asymptote come from? Anyone know? How do you get that vertical asymptote number? X values of no one? The denominator? Zeros? Maybe? Okay, all right, here we go. Let's try it then. Let's say this. F of x equals, let's do this. Let's consider that to be at x equals 2. 3 over x minus 2. Factors of the denominator only is a vertical asymptote, and it comes from factors of the denominator only. So I'm just going to sketch the rest of this picture because I have it. Okay. So it would be up here and here. Notice that I didn't really label any other scale. I just showed the vertical asymptote. Okay. A point or a removable discontinuity is an open point. Okay, right? It's a point. It's an X and a Y. Sometimes we call this a hole. Okay, so f of x equals let's factor and reduce that ratio of polynomials. Right? We did a little preview so that we could do a little bit of our arithmetic with polynomials. Okay? Notice that the x minus 4 cancels out. Okay? So I'm going to cross it out. And I am left with x plus 4. Okay. And we're going to draw a graph so I can show you what a hole would look like. Yeah, isn't that just a line? It is just a line. I'm going to move it over to quadrant 1 for myself. 1, 2, 3, 4. 1, 2, 3, 4. Don't get too far ahead of me. Oh, I guess I should have left it there. I got it. I know what I'm going to do. There we go. 1, 2, 3, 4. And it goes up like this, right, with a 1 slope. Okay, here's what your hole looks like. It literally looks like an open point on the graph. That's what it looks like. Now I'm going to label the coordinates because a hole is coordinates.
How do you tell where the hole is?
Good question. It's going to be at x equals 4. Look at which factor canceled out. Nope. Positive 4. Positive 4. 8. Plug in 4 to what's left. So it would be at 4, 8.
Where are we dropping?
Okay. So where does this hole come from? It comes from the common factor of the numerator and the denominator. Because it crosses out. Yeah. Question. Hold on. Let's write this and then I'll say it again. Okay? Comes from common factor of numerator and denominator. Then there would be no hole. Right? Just like the first 6 questions we graphed today, there is no factoring, there's no common factors. This only happens, okay, most things that we do algebraically have a visual representation. If algebraically we get a common factor, it will be represented by an open hole in the graph. Just like a factor of the denominator only is represented by a vertical asymptote in the graph. Yeah. Yeah. Okay, so where does that hole come from? So it's an open point. Let's say that we'll come back and write it. No discontinuities means no holes, no asymptotes, no vertical asymptotes, no vertical asymptotes, and no breaks. Sometimes we call that a jump. Which means the denominator, no common factors, and there's no zeros of the denominator. Yeah. Yeah, we're going to do 2 of those examples on the next page, and then we'll come back and write it. Because I think if I write it first, it won't make sense. So we'll come back and write it right after we do the example. Okay? Means denominator has no zeros. That's denominator has no zeros. No common factors of numerator and denominator. So we basically just said there's no vertical asymptote, right? No zeros of the denominator, and no holes, no common factors of the numerator and denominator. That means that there's no discontinuities. Yes? Depending upon the graph, yes. Could be polynomial, quadratic, absolute value. There are some ratios of polynomials that will have no vertical asymptote and no holes. It could happen. Okay, that's maybe the day 3 graphing. Okay, we're going to do 2 examples with the hole because that's really the quantity. That's what I want you to learn today is the hole.
So,
yeah. We're going to come back and write a second sentence about the hole, but I want to do an example with it first.
So the vertical asymptote, that's just like what we've been doing.
Yes. Yes. Okay. Here we go. Flip. Okay. Here we go. Factor the top, factor the bottom. That's what I want you to do. Factor the top, factor the bottom. And then we're going to find exactly the same quantities we've been looking for. Okay, so we need vertical asymptote, horizontal asymptote. We need x-intercept, y-intercept. But I'm going to add whole. Right? I'm going to add whole, which is just an open circle. It's just an open point. I'm going to put it right underneath x and y intercept because it's a point on the graph. It's just an open point on the graph. All right, looking at this, I notice that this factor reduces. Okay, right? Factor, reduce. Let's look at what we're left with. Okay. That's a AHK format. A is 2, H is 2, K is 0. Okay, well, let's see what we can do. Vertical asymptote, x equals 2. Horizontal asymptote, y equals 0. Okay. So it looks like there's going to be no x-intercepts because of where that asymptote is. Okay. Zero equals 2. Just none. Right, algebraically, it would not solve. Okay. Y-intercept. Okay, so -1, 0, -1. Okay. Whole. So the question was, where does the whole come from? Look at the crossed out factor. Yeah.
So when you were writing whole, would you just put like x equals -3?
Yeah.
Or would you
We're going to find x and y. We're going to find both because it is a point on the graph. It's just an open point, right?
Oh.
That was a closed point. This is going to be an open point, so I want to put it in the right place. But yes, it is at x equals -3 because it comes from the reduced factor. Now look at this. This one's a vertical asymptote. Okay. This one is the vertical asymptote, the factor of the denominator. This one is the whole. Notice how that gives me the asymptote of +2. It's opposite. Same reason. This gives me an x-coordinate of -3. It's opposite. So we're going to say x equals -3. That's where it comes from. The factor that reduced from the top and the bottom. How am I going to find my y-coordinate? You're going to plug it in. You're going to plug it in. Notice, though, everything is coming from that reduced version. Once you reduce it, do not go back. So -2/5, correct. So -3, -2/5. -3, so kind of small. So it's right there. It's just an open point on the graph. And then connect, right? We already know the basic shape. Quadrant, top right, bottom left. I can see my stretch value, so I could get a couple more points if I needed them. Whoop, look at that. I had to pick my pencil up. That's because it's called a discontinuity. I had to pick my pencil up to draw it. Okay. Right there is my, I reflected, and I used my 2 count. The last step is always any more points you feel is necessary, right? If you don't have enough points to sketch the shape, you plot an extra point. I'm using my 2, my stretch of 2 to get those. Okay.
What's the whole mean? Why is it there?
Because the x-coordinate of -3 comes from the reduced factor. So look, I'm at the x-coordinate of -3, and I plugged it in and I got -2/5. It's going to be on the graph.
Why a hole?
Because visually, okay, a reduced factor appears as a hole on the graph. Right? That's how it appears, yes.
So would you write the domain with 3 different?
Yeah, your domain would have 3 pieces. Starts getting a little tedious, so we're going to do it 2 ways today. Okay, domain, -3, -3 to 2, 2 to positive infinity, such that. When you start getting a lot of discontinuities, it gets kind of slow to write it this way. And so that's your set notation. X such that x cannot be -3 and +2. Look at you where you had to pick up your pencil. They're called discontinuities. Every discontinuity has to be taken out of the domain. -3 for the whole, +2 for the vertical asymptote. Okay, range. You got to look at your graph carefully for range. Oh, I should have. I'm going to write it right. It gets kind of tedious after you have more than one break. It's kind of slow, and so either notation is acceptable. Either notation is acceptable. Okay, so we get x plus 3, x plus 3, x minus 2, x plus 2. Oh, all right. No common factors. Okay. Let's continue. We need vertical asymptote, horizontal asymptote. I'm trying to think if I meant for there to be a common factor.
2 minutes back.
See if we can avoid that. Okay, much better. No, it's not. Okay, let's go. Let's reduce. Plus 3. So we end up with x plus 3 over x minus 3. Now, I'm going to start labeling the factors that I see and what they give me. This one's going to give me a vertical asymptote because that denominator factor doesn't reduce. This one is going to give me the whole because it does reduce. The numerator factor, okay, numerator factor. Polynomials, how do you find x-intercepts? You factor them. This one's going to give you the x-intercept. All of the factors give you something. I'm going to label them right there. Okay. plot what you have, right? Let's list what we get. We have a vertical asymptote, x equals 3. Horizontal. Oh, okay. What was our conclusion from our warm-up today? I don't really want to divide this, right? So I'm going to see if I can do it without, yeah? Yep. And leading coefficient of the denominator, what's that ratio? 1. If you don't have to put it in AHK, don't. You don't have to. See if we can do this without. Okay, so I'm going to put my asymptotes on that I have. So I have a 3 and a 1. Okay. I'm going to start listing my points, x-intercept, y-intercept. It's going to take no solving, but I'm going to do the solving anyways. I'm going to do the solving anyway so that you can see what I mean by the factor of the numerator. Cross multiply. Oh, I should have just taken the -3 and plotted it because it matches the factor of the numerator. Okay, y-intercept. Okay. 0, -1. Oh, that's probably enough points to draw the shape. Even though I don't put this in transformation form, it's going to have the same shape. So it's going to be in the bottom left quadrant, top right quadrant. I'm going to connect my dots. Right, you only need 1 point per branch. If you have more, great. Hole. Right, because I do have a hole labeled up here at the top. I do need to find it. It's just an additional point that is an open circle. X equals +3. Y equals 3 plus 3. Oh, it's at -3. Sorry, -3. I just did something weird. I feel like something weird just happened. That's okay. No, that's all right. Let's keep going. It is -3 though. -3. -3. Oh no, we're good. We're good. So it's just y equals 0. So it's at -3, 0. Oh, okay. Well, that's a little bit weird. It seems to be overlapping my x-intercept. Well, guess what, guys? It's a hole. It's going to be a hole. Yeah, these two things happen to be overlapping because of how we had some common factors up here. You cannot, discontinuity overrides it, okay? Any discontinuity will override any point that you think you're supposed to be graphing. Okay. I'm going to put a very light because it's a discontinuity instead. The work is not wrong, and I wouldn't know this until I get all the way done trying to find the hole, that the hole is going to override what I thought was an x-intercept. Okay? And so I'm looking up here. I cannot have, I'm going to do my domain, -infinity in order, negative 3, negative 3 to 3, 3 to positive infinity. So I'm going to do this one. X can't be. Look at where I started. Vertical asymptote hole. Those two things are discontinuities. They will be taken out of the domain. So no matter what, that's going to be a hole, that's going to be an asymptote. Regardless of whatever else you find. The discontinuity is like wins. Range. Oh, I still need to graph my other portion.
Negative 3 isn't going on the graph, so what is
Yeah, it's not. Why?
I'm sort of confused as to why we did negative 3 and 3 rather than listing the coordinates of the whole, which is...
This is the coordinates of the whole. Well, this is the x-coordinate. This is the y-coordinate.
Why do we have a 3 instead of...
This is the whole. This is the vertical asymptote.
Oh.
Okay, so let's
So
do our
it's
range.
That and that, okay.
So 3, 2, 3, 2. I'm going to reflect my points. Yeah, points reflect over the quadrants. 3, 2, 3, 2. Yeah. I looked at what was already here.
I know, but how'd you get that one?
That was my y-intercept.
Oh, that was your Y.
Yeah, you can, any point reflects over. You just count the same way.
So when you found the Y-intercept, you saw 3, 2, and then you just...
Yeah, so look at this one. 1, 2, 3, 4, 5, 6. Oh, my stretch value is 6. Because that's a 6, 1. Same diff, right? Okay, range, negative infinity. 0, union, 0 to 1, union. Do I care which notation you use? No. You use whichever one is faster to write.